Greetings and welcome back. Today we'll be looking at reduction reactions for organic compounds. Reduction reactions are those that either add new bonds to H or remove new bonds to oxygen or nitrogen or halogen. So for example, a ketone can be reduced by removing bonds from carbon to oxygen and adding bonds to hydrogen by converting it into an alcohol. So what we see here is that this carbon right here no longer has two bonds to oxygen. It now has one bond to oxygen and one bond to hydrogen. So therefore we would say that that carbon has been reduced, or a shorthand way of indicating that is putting brackets around an H. The other way around would be to say that that guy has been oxidized. Oxidize means to remove bonds from hydrogen or add bonds to oxygen, and therefore we would sometimes use the convention of an O in brackets to say that the other way around, converting an alcohol to a ketone, is an oxidation reaction. We'll be looking first in this video at reduction reactions, and then in the next companion video we'll be looking at organic oxidation reactions. To revisit that reaction with its reagents, we could just look at the fact that a carbonyl has an electrophilic carbon at the bottom, and therefore it would react like with a nucleophile. If we want to convert it into an alcohol by reduction, what we can do is add a hydrogen nucleophile, or an H-. Usually this would be in the form of lithium aluminum hydride or sodium borohydride, which acts as if it is an H-. The mechanism would be that the H- attacks the electrophilic carbon and kicks electrons up to the O. That would make an O-, and therefore in order to protonate it into an alcohol, we would use some water and or a little bit of acid, and that would just turn that O up there into an OH. So this LAH followed by water is one of the main ways in which we reduce not just aldehydes or ketones, but a variety of functional groups. For instance, amines. Amines are carbons double bonded to nitrogen. That nitrogen could be attached to whatever, but that group right there has, just like the carbonyl, an electrophilic carbon down at the bottom. And therefore we could reduce this by adding LAH followed by water and or a little bit of acid. The LAH acts like an H-. The H- would attack the electrophilic carbon, kick electrons up to the nitrogen, and give us a brand new single bond to a hydrogen at the bottom and convert the double bond N into a single bond N. That would give us momentarily an N-, or really an N attached to aluminum, but we would then protonate that to make it into an NH. And so therefore we would reduce down that nitrogen into an NH. As it turns out, this reaction is one of the best ways to make amines. So we've looked at synthesizing amines previously in this class, but nothing that worked tremendously well. The way that you can turn a carbonyl into an imine and an imine into a reduced imine, which is what we see on the right over there, just an amine, is really one of the best ways we have to make amines. And so this can be used to make primary or secondary or even tertiary amines, and this is sometimes called reductive amination, because you make an amine by reducing an imine. So reductive amination is a really good way to synthesize an amine. Primary, secondary, or even tertiary amines. All right, so let's keep going. We also have a functional group that is produced by an alkyl halide plus cyanide. Cyanide would attack an alkyl halide, kicking off the halogen, and give us a nitrile. A nitrile is a C triple bond N. So just like we could reduce a C double bond N with LAH followed by water, we could also reduce doubly C triple bond N by adding LAH followed by water or acid. This would turn that C triple bond N into a C single bond N and add two hydrogens on the carbon and two hydrogens on the nitrogen. So this is another good way to make a primary amine, but note that from the starting material, which only had let's say R number of carbons, if that had 4 carbons, the product would have that number plus 1 more. So we don't just add on the amine, we actually add on an amine plus a carbon. But this is another example of how we can reduce a carbon-nitrogen functional group, in this case a nitrile. We can add 2 hydrogens to this carbon and 2 hydrogens to that nitrogen, and we therefore get rid of the pi bonds and replace them all with hydrogens. All right, next let's look at an amide. An amide is a C double bond O NH2. It could be NH2, it could be NR2, it could be NHR, but we have a little bit of flexibility on what could be over there. Regardless, the amide is this part right here. It's this C double bond O attached to a nitrogen. We can reduce that using LAH followed by water or acid. And in this case, we would reduce down the entire functional group to simply an amine. So that carbonyl would turn into a CH2, NH2. So what we'll notice that in this case, what we've done is we've removed actually 2 of the 3 bonds to heteroatoms. So once again, this carbon has 2 bonds to O and 1 bond to N. We can't end up removing every bond to a heteroatom, but what we can do is through the use of LAH, it will completely cleave off that oxygen as water and leave us with just 1 bond to a heteroatom, that is to say nitrogen. So notice that starting at the top, we go from a carbon with 2 bonds to oxygen to a carbon with 1 bond to oxygen. We can go from a carbon with 2 bonds to nitrogen to a carbon with 1 bond to nitrogen. And in both of those cases, we're replacing that bond with an H. With a nitrile, we go from a carbon with 3 bonds to nitrogen down to a carbon with 1 bond to nitrogen, replacing the other 2 bonds with hydrogens. And lastly, with the amide, we can turn a carbon with 2 bonds to oxygen and 1 to nitrogen down to just 1 bond to nitrogen, and we replace both of those oxygen bonds with bonds to a hydrogen. So both of these reactions down here actually give us other ways to make amines. Through the cyanide reduction, we can make a primary amine. And through the reduction of an amide, we could make an amine that could be primary or secondary or tertiary, depending on how many R groups are attached over on this side. The final reduction that I'll show you, which involves nitrogen, is a Nitro Group, or an RNO2. This is often used with a benzene, so a nitro aromatic ring is a very common thing to be able to produce. And we can reduce that down to an NH2 or an amine. In truth, there are very many ways to reduce this. The first is one that we've seen already, which is hydrogen and platinum or palladium. We would add hydrogens and completely convert that NO2 down to an NH2. Another way to do this is with hydrogen from the form of an acid and a metal. Metals like to convert into metal plus charges, or a metal 1 or a metal 2, meaning that they give away electrons. And so in effect, this set of reagents right here would be similar to an H minus in that zinc would give away electrons, H plus would supply the protons, and we can essentially add on hydrogens instead of oxygen. This is an or in that you could use one set of reagents or the other set of reagents, but in either case, reducing a nitro to an amine is not nearly as useful as the ones above. However, if you find yourself with a nitro, you can of course convert that down to an amine as well through a reduction reaction. The final reduction that I'd like to show you involves converting an aldehyde or a ketone all the way down to an alkane, meaning that it has been reduced not just once to form an alcohol, but twice to completely eliminate the oxygen. There are 2 different ways of doing this, one in acidic conditions and one in basic conditions, and I'd like to show you both. The first, under acidic conditions, involves using zinc and H+. Oftentimes, a little bit of mercury is added into the zinc in order to facilitate the reaction. However, just like we mentioned for the nitro group, essentially what this is doing is the zinc or mercury metals will supply electrons, the acid supplies the hydrogens, and we're able to completely reduce this all the way down to an alkane. This doesn't change the number of carbon chains, and therefore this is simply a functional group interchange in which a carbonyl from a ketone or an aldehyde can be completed or converted completely down to an alkane. This reaction is called the Clemmensen reduction, as it was discovered by a Danish chemist named Clemmensen. Clemmensen reduction. We have another way to do this reaction, which is to convert that C double bond O to the alkane using first hydrazine, which is NH2NH2, followed by base in the presence of heat, usually KOH. This is named the Wolff-Kishner reduction after two chemists, Wolff and Kishner, one who was Russian and one who was German, who discovered it about the same time. But once again, it will completely reduce the carbonyl down to an alkane. The mechanism of this one down here is known very well, and that's one that if you're interested, we can try to work out in class. You might notice that the first step will convert the C double bond O into a C double bond N, and eventually what will happen is that this will produce nitrogen gas, meaning that that will irreversibly come off and gives us very good yields. All right, those are our reduction reactions for today. Let's practice that a little bit more, and I will see you in class.